Hello and welcome back to the 8-bit CPU. After a longer pause, I was able to upload the next video finally. And so today we're going to have a look at the final part of the hardware in this CPU, which is the control unit. And the control unit is implemented in these two breadboards, plus some of the chips on here. And so the computer at the moment is running this very simple Fibonacci program. So it simply sums up the last two values in the series, and you can see the Fibonacci numbers appearing here. And so what the control unit does is it uses all of these blue LEDs here, which are in fact control signals. And in order to execute the instructions of our program, it needs to set these control signals at various times to signal the other parts of the computer, such as the registers, the ALU, the memory, to transfer and perform operations on the data, which is moving through the bus. And so that's how the CPU coordinates the action of the other components in the CPU in order to execute these instructions. And so let's slow down the clock so we can have a closer look at what is actually happening. So I'm going to slow it down to as far as we can. And so you'll see that for any particular instruction, so right now we're actually on the instruction, we're moving pretty quickly, so we're at instruction 4 here, which is this add instruction. And so, okay, we're actually on to the next one already. But anyway, any of these instructions, when we want to execute it, we're going to have to perform several different steps. So we're going to have to first actually fetch the instruction contents, which are these bits here, from memory, from program memory. And then we're going to actually have to do some things. So in this case, we'll have to go and get some register values from the C register, get those out on the bus, tell the ALU, as we saw in a previous episode, to perform an addition, and then go and get the result from that addition and stick it back into the C register. So every instruction requires a series of steps in order to complete it. And so the way we organize those steps is we have what we call microcycles here. So we have different micro times, which we denote with a capital T. And so they run from 0 to 7. So it's a 3-bit number. And as you can see here, in fact, these LEDs are mounted backwards. So it's counting from left to right. So that's 2. Then it went back to 0. There's 1. There's 2, 0 again. And so different instructions will actually require a different number of steps to complete. And so some of them will have 3 steps. Some of them will have even 4 or 5 steps. And here's one that has a T3, and then it resets. And so we have a maximum possible number of steps of 7. So this counter is capable of counting all the way up to 7. And we'll see in a minute how it organizes the fact that some instructions don't need 7 cycles. And so what happens is if I let it run to the beginning of an instruction, such as here. So now we're on time T0. So this is the very beginning of a new instruction. And so the instruction which is about to be executed is this instruction here at address 9. So let's have a look at address 9 in my program, and we can see that's this move instruction. So move the contents of the A register into the B register. So how is that going to work? Well, as you can see, the control unit is at the moment asserting 2 control signals. So there's this program counter enable and the memory address register write. And so this timer, which is at time T0, says that at time T0, what we need is to get the contents of the program counter into the memory address register. And of course, the reason for that is we actually want to go and get the instruction, which is this byte here, and put it into the instruction register. And so the control unit on this time Z0 has set all of its control signals to the correct values. So 2 of them are being asserted right now, and all the others are not asserted. And so the idea of that is that on the next rising clock edge, a data transfer will actually occur from the program counter, which is here, through the bus into the memory address register. So as soon as my clock goes high, when we will have a rising edge, that transfer will take place, and so this value will be latched into the memory address register. But as that happens, I want you to pay very close attention to what's happening to this timer here, to the microcycle number that our CPU is on. And so that should also then move from 0 to 1, because that's all it needs to do on time t0. So on time t1, it'll need to do something else. And so I want you to realize when this timer counts. So let me just quickly advance the clock. So what will first happen is that will move into the memory address register. There it is. And hopefully you saw that, but this counter counted from 0 to 1 on the falling edge of the clock. So as soon as that went high, this counter remained at 0. And so these control signals were still asserting their correct value for time t0 at the moment of the rising clock edge when this data transfer from the program counter to the memory address register occurred. And after that was complete, well after the end of the rising edge, so while this clock was high, and in fact at the moment when it went low again, that is when this counter increased from 0 to 1. And so after that counter increased, now of course these control signals changed as well, because the way this works is that these EEPROM chips are being addressed by, on the one hand, the contents of this instruction register, and on the other hand, these 3 bits, which constitute the particular time at which the particular part of the instruction cycle I want executed next. And so at this time t1, what will happen is something else here. So we'll see that memory is enabled. So whatever is in RAM is being put out onto the bus. And in fact, program memory is being enabled because the control unit is telling the RAM chip to assert this program memory bit. And so in fact, this byte which we have here ought to be the byte at address 9 in program memory, and yes it is. So that's 00001000. And then finally, the instruction register write signal is being asserted. So once again, these contents which are coming from memory, which are now on the bus, they will get latched into this instruction register when the next rising clock edge occurs. And so when that happens, this byte will go into the instruction register, but this timer won't increase its value until the clock falls again. So at the rising edge, this will go into the instruction register, and on the falling edge, this counter will increase to 2. And so at that point, the control signals will change. And so what we want to achieve is that we're working in pairs. So on the rising clock edge, data is transferred through the bus from the various components to some other components on the computer. And on the falling edge, the control logic is changing and is asserting a new set of data transfers which are to take place on the following rising clock edge. And so we're constantly alternating between this data transfer and control logic change. And that's the way we keep everything nicely synchronized, and that's the way we make sure that these data transfers occur cleanly, so we don't have control signals which are fluctuating during the rising clock edge, and that's very important. And we'll get to that a few times during this video. So anyway, if we allow the next rising clock edge, what we'll see, so we'll get that value into the instruction register, and then on the falling edge, this counter will increase again. So there's the rising edge, and there was the falling edge. Now we're at microtime 2 here, T2, so this is a 2. And so now that this instruction has been loaded into the instruction register, the control logic is in fact asserting yet another series of signals. So in this case, that is the register A enable control signal, which is going to the A register here and instructing it to output its contents onto the bus. And so here they are. This is 233 in binary. And also the B register write signal is being set by the control logic. And so this B register on the next rising clock edge will take that value which is on the bus and latch it into its register. Now there's another control signal which is being asserted, which is this one here. And so this one is a timer reset, is what that stands for. And what that's going to do is that's a signal which loops back inside the control logic to this timer. which is in fact implemented on this chip here. And now this is the 74HCT161, which we've used a few times before. We've used it here in the program counter, and we've also used it here for our decimal display. And so that's that same timer, which, as you hopefully remember, has a clock signal which goes into it, which tells it when to perform its increase. Now, of course, as we've been saying, this particular timer is wired up such that it actually counts on the falling clock edge, not on the rising clock edge. And we've done that so that these control signals actually stay stable during the rising clock edge, at which point the data transfers from the various components using the bus take place. So the way that's done is that if you remember right in the beginning of the series, we talked about this clock module. In fact, the very last step of the clock module was to perform an inversion, because we were using NAND gates. And so in the very last step, we needed to invert the result to get the actual clock signal. And so if I connect this final signal from these NAND gates, which is in fact this white wire here, then that is the inverse of the clock signal. So that is actually high right now. And so that is the signal that's going into this timer. And so this timer is now receiving an extra signal, which is this reset, which is being set from the control unit. And so what that does is that's asserting another control signal on this timer, which will reset that timer back to 0 when it receives a rising clock edge. But of course, it receives a rising clock edge not when our actual clock is rising, but when the inverse of our clock is rising. In other words, when the clock is falling again. And so this chip, when the next falling clock edge arrives, rather than continuing to count, it will actually turn back to 0, because the control unit is asserting this timer reset signal. And so by programming our control unit to, first of all, perform the operation, at the last cycle of any operation, if we add this control signal, what that will do is it will automatically reset the timer. And so for this particular instruction, we have 2 instruction load cycles, and then we have 1 further cycle to perform the transfer from, in this case, the A register into the B register. And so we can set that reset signal immediately. But some other instruction might require 4 or 5 different cycles. And so on the last cycle, if we program our control unit in such a way that on the last cycle we always assert that reset signal, well then we'll be able to reset that clock and prevent it from counting all the way up to 8 because we'd waste instruction cycles that way. And so that's the meaning of that final signal, which is being set here. So if I advance the clock again on the rising clock edge, that 233, which is this value in binary, will be latched into the B register. And then when the clock falls again, that timer, instead of counting to 3, it will actually count to 0. And so at that point, we'll once again get the control signals up here, which correspond to a time t0. So let's try that. And so there's the rising clock edge, and there's the falling. And so that went to 0 back on the falling edge. And the value that was here, this 233, has gone into that register. Of course, now the bus is asserting something completely different, because on the falling edge, we've asserted a different signal. And so now the program counter is once again being enabled on the bus. Now, there's another slightly delicate, but nonetheless very important aspect to realize about the control logic. So we've just finished executing this move instruction. So move the contents of A into B. So B now contains the same value as A. And so the next instruction is going to be this jump. And that's located at address 10. And so 10 here is asserted because when we were loading that instruction, the program counter was told to increment, and so that's now at a value of 10. But the instruction register still contains this move instruction here. And so when we are starting the execution of the next instruction, which is this jump instruction at address 10, we don't actually know yet that there is a jump instruction there. In fact, we have no idea what instruction is there. It could be absolutely anything, and that will depend purely on what lands in the instruction register after the first 2 cycles, which go and fetch the actual instruction from program memory. So this time t0, the fact that these two control signals are asserted, that cannot in any way depend on the contents of the instruction register. Or said in a different way, no matter what instruction is in this instruction register, in order for the control logic to be able to load the next instruction, which at this point is not known to it, these sequences here, this instruction loading sequence or instruction fetch sequence, must be fixed, must be the same for every possible combination of bits here in the instruction register. Or put even another way, for all possible instructions, the first two microcycles are all the same. They have to be. That's the only way to guarantee that no matter what is in here, we will actually be able to load the next instruction. And so those two cycles are, on T0 we have program counter enable and memory address write. So we'll put that 10 into there. There it is. And the T1 is also fixed, cannot depend on what's in this instruction register, is memory enable, program memory on, instruction register write, and all of that will ensure that the contents which are in program memory at the address which we just loaded actually land in the instruction register. And one final signal, which is this program counter count, which will tell the program counter to increase by 1. Those four signals also must be the same on time T1 for every possible instruction which might be in our instruction register. And so that's a very important point. And we can't say that for some instruction maybe we could optimize the loading because it's the same as before or whatever. We can't do any of that because we don't know what the next instruction is. And so in fact, in order to load this instruction at address 10, this jump instruction, the T0 and T1 information or control signals which are being asserted are actually being asserted by the previous instruction, which could have been anything because that previous instruction is still here in this instruction register. And so the only way to make that work in a predictable way is to simply have exactly the same control signals for every possible instruction programmed into those EEPROMs. Now the main component of our control logic is this EEPROM chip here. And so we're using the same EEPROM chip that we used for the decimal display. And so that's a 4 kilobyte or a 64 kilobit chip. And so it outputs 8-bit values. And so that's these IO0 all the way to IO7 lines. And so we've connected those to control signals. And so in fact, one of these EEPROMs is able to manage 8 different control signals. And since we have 27 control signals, which we need to manage, that means we need 4 of these EEPROM chips. And Ben Eater, I think, has 15 control signals, and so he can get away with just 2 of them. But our computer is quite a bit bigger. We have 4 registers, and our ALU uses at least 5 control signals, so we need quite a bit more. So that's why we have, first of all, 4 of these. Now, secondly, since this is a 64 kilobit EEPROM, we actually have 13 different address lines. So we have A0 to 7, 8, 9, 10, 11, and 12. So that gives us 13 possible address lines. And so the way that this EEPROM works is we have a series of states, let's say, on the input into our control logic. And those are, first of all, most importantly, the instruction register. So the bits which are in here, which on our computer are 8, really every single one of these 8 bits is important and is part of the instruction. And also this micro time, so this particular time cycle that we're on. And so that's 3 bits. So that's a total of 11 bits on the input, and every single combination of those 11 bits will in fact require a particular setting of all of these control signals. And so, for example, on this T1 of this move instruction, but as we just said, as in fact for any instruction, for those particular bit values of a timer 0, 0, 1, and any combination of bits here, we need to assert those signals. And so on this first EEPROM chip, we need to assert that signal. On the second one, we need to assert none at all. On the third EEPROM chip, we need to assert these two, and on the last one, we need to assert this single signal. And so for another time and another instruction, we might have another set of signals which need to be asserted. So if we program these EEPROMs to put out the correct control signals when we have the correct inputs, i.e. timer cycles and instruction, well, then that is in fact the microcode of our CPU. Then that's how our control logic will drive these control signals. Now, I've left out one very important part. So we're using 11 signals right now, but of course we have also in this computer a set of conditional instructions. And so a conditional instruction is, for example, this jump carry here. And so what jump carry will do, which turns out to be this in binary, jump carry, once it's been loaded into the instruction register, it will need to look not only, or the control logic will need to look not only at those bytes in the instruction register, but it will also have to go and check whether the carry is set. And whether or not the carry is set, that's available here on these ALU flags, which we latched in the ALU, on the last ALU operation. And so the control logic also, in fact, needs to be aware of the flags, and we have 4 of them. So naively, that would mean that we need 3 timer input bits, we need 8 instruction register input bits, and we need 4 flags. All of those would be input bits for each of our EEPROMs. And so that's 3 plus 8, which is 11, plus 4, that's 15 input bits, which we'd need. And those would control the 27 output bits, 8 on each single EEPROM, that we're actually sending onto the control signals. But we don't have 15 pins, we only have 13. And so we can't actually use all 4 of these flags. And so we need to go into find some clever way of getting around that. And so as it turns out, we're in fact only using 2 of the address pins, and we're using some sneaky combinational logic to get away with that, to be able to drive the control logic actually only accepting 2 different bits coming in from the flags register. But so in general, the flags, the state of the flags, are an equally valid input into the control logic, just as this timer cycle, the particular cycle that we're on, and the instruction register. So we need to keep those in mind. Now, one way of solving this problem is to think for a moment about the kind of conditional instructions that we will be implementing. And so some of the first which we saw were these add and subtract with carry instructions. So the way they will work is they will perform an add of this register with the B register, and they will additionally add whatever the carry flag is. So what that means is that they will need to set the carry flag in the ALU if the carry flag in the flags register is set, and they will not set it if the carry flag is not set. So in fact, this instruction will differ by 1 bit depending on the contents of the carry flag. So in that sense, it is a conditional instruction. The same applies to this subtract instruction. So it too will subtract the B register from this register and write the result back. And it will additionally not subtract, i.e. not borrow, if the carry flag is set, and if it isn't set, it will borrow. And so once again, it will do that based on the contents of the current carry flag. And so that will then set or not the input carry to the ALU. So that too is a conditional instruction. So depending on whether the current carry flag is set or not, it will instruct the ALU differently. Now, the other conditional instructions that we're interested in are, of course, the conditional jump instructions. And that's these. So we have a jump on carry, and if carry is set, then we should jump to some immediate address, which is located in the program code. And we can do the same for the other three flags, for the zero flag, the negative flag, and the overflow flag. So we can have a jump instruction corresponding to each one of them. And so what you'll notice is that there are three different instructions which need to take into account the contents of the carry flag. But for all the other flags, there is really only one instruction that we're currently thinking of, which is this jump instruction based on the contents of that flag. So the idea here is if we can somehow, in our EEPROM chips, channel the contents of whatever the flag is that we're interested in into this final address line 12, then we could sort of multiplex it and use it for all three of these flags. And so what we'd need to do then is this jump 0, this should really only jump if the 0 flag is set. So if the negative flag or the overflow flag are set and the 0 flag isn't, then it shouldn't jump. And the same applies for this instruction. But none of these instructions depend on two flags. So there is no instruction, we're not planning on supporting an instruction which says jump if negative and overflow. We don't have such an instruction. And so the plan is to use that to our advantage. So what we could do is we can try and encode these instructions in a special way. And here is the way I've gone with. So first thing to note is this is, if you look back at the video on the instruction register, then we go into how we come about these binary encodings. So what this says is, in fact, it's a move instruction into an immediate operand, which is nonsense because you can't move into an immediate value. And so we're abusing these or assigning new meaning to these instruction encodings, which otherwise wouldn't make any sense at all. And we discussed doing that in our video about instruction register. And so we've chosen to use the move into immediate instruction to encode these conditional jumps. So the first one, the jump on carry, I've set that this way. And so we can actually use one of the two address lines which we have over. And so we'll use A11 to directly connect that to the carry flag. And then by doing that, we'll also be able to implement these easily enough. So we no longer need to worry about the carry flag. So we're just left with these three. And so what we've done here is I've made sure that we have these last three bits in the instruction organized in such a way that a conditional instruction which should consider the condition to be fulfilled only if the 0 flag is set always has 001 at the end. I've ensured that in my instruction encoding. And the negative flag always has this second bit set and none of the others. And the overflow flag has this third bit set and none of the others. And what that allows us to do we can see in here. So I have a bit of combinational logic here where I am taking the last three bits of the instruction. And so we said that if we want to check for 0, for the 0 flag, we need that last bit in the instruction to be set to 1. So I take this least significant bit of the instruction and I AND it together with the 0 flag. And so the result of that will only be a 1 if we're actually dealing with an instruction that is interested in the 0 flag. So if we're dealing with this instruction, then even if the 0 flag is set, the result of this AND gate will still be 0, because that least significant bit for that instruction is 0. Now, for the second bit, which corresponds to the negative flag, which is this bit number 1 here, we're ANDing that together with the negative flag. And so the output of that AND gate will only be set if both the negative flag are on and we're actually interested in an instruction which should conditionally execute on the negative flag. And we do exactly the same for the overflow flag. We link that to bit number 2, to the third bit of the instruction. And so then we take any of these bits will only ever be set if both the flag and the corresponding bit in the instruction register are set. And in all other cases, those bits will be 0. And so if we OR all of those together, what we have is a single flag's input, which will be 1 if and only if we are either executing a 0 instruction and the 0 flag is set, or executing a jump negative instruction and the negative flag is set, or executing a jump overflow instruction and the overflow flag is set. And so in all 3 of those cases, what we need to do is the same. So we can code our EEPROMs in that case to actually perform the jump. And in all other cases, when the output from all of these ORs is a 0, we shouldn't jump. And so we can actually, in the control logic, consider this to be a single instruction, jump on flag. And the determination of which flag is set and if it corresponds to the correct instruction is then handled by this little bit of extra logic which we've built in here. And so that allows us to use a single line which we connect to the 12th address pin on all of our EEPROMs. And so that's how we get away with having only 2 pins left and nonetheless taking into account our 4 different flags. And so the reason we're able to do that is because we don't support arbitrary combinations of flags in our instructions. We've chosen very specific conditional instructions which allow us in fact to multiplex the single bit which indicates the condition of that flag being set or not. And so those gates, those AND and OR gates which execute all of that logic are located down here. And so the result of that is a single input line into bit 12 of the EEPROMs. Now there's one more aspect about this control unit that I want to talk to while we're still talking about the hardware. So as at this particular time we're on instruction cycle T1, and so what's going to happen on the rising clock edge is that the contents of the memory, which have been pointed to by the program counter, to read the next instruction from program memory, which is the instruction at byte 10. So that's this jump instruction, which is there and is in fact already out on the bus because we've enabled memory. That will be latched into the instruction register on the next rising clock edge. Now we've taken great care to ensure that this particular clock will only advance from 1 to 2 after the clock falls again. And the reason we do that is because we want these EEPROM chips to be totally stable during the rising clock edge so that the control signals going to the other parts of the computer are stable, and it will allow those components to actually work reliably when that rising clock edge arrives. And in fact, if we look at the data sheets for this EEPROM, for our EEPROMs, we'll see a bit later here when they talk about reading. After we set the address, which in our case consists of, this timer here, and the instruction register, and these flags, so the carry flag directly, and the other flags through this combinational logic here. So when we set all of those bits, there's a particular time that we need to respect before the output, i.e. the control signals, are actually valid. That's this TACC here. And so we can see that this is a real value. So we need to wait until 150 nanoseconds after all of those signals have been set before these control signals can be guaranteed to contain any kind of value. So if we fluctuate these addresses at some point, then 150 nanoseconds after that, these control signals could theoretically be anything at all. There's no guarantee that they will be the correct control signals that we want to send to our components. So this really is a very strict requirement that these inputs, all of these inputs which go to the address lines of these EEPROMs, they cannot absolutely under any circumstance vary during the rising clock edge. because then we'd be out of sync for 150 nanoseconds, and so God knows what, anything at all could happen. And so in this particular instance, on this time 1, on the rising clock edge, that value will go into the instruction register. But of course, the instruction register is providing 8 of the 13 address inputs to these EEPROMs. And so as soon as the rising clock edge arrives, that value will go into the instruction register. Those address lines will change. And so for 150 nanoseconds after that, these control signals will be undefined. They could be anything. And so they could disrupt the operation of our computer. In fact, Benito doesn't really take care of that. So he has exactly that situation where on T1, his new instruction is going into the instruction register and is possibly disrupting the operation of his EEPROMs. He only has 2. And so the control signals could send out short pulses of nonsense for a certain time. So for my EEPROMs, that time is 150 nanoseconds. Now, for whatever reason, he never runs into that problem, but another YouTube user, David Courtney, has described exactly that phenomena, and he does some measurements with an oscilloscope, and he finds that particular EEPROM chips behave slightly differently. So some of them actually have very high peaks and cause control signals, for example, on a counter signal, or I think in his case, his output register latches a value when it shouldn't do. And then he changes that EEPROM chip for another one, which has slightly different electrical characteristics. And so in that case, the peak is not high enough to trigger that behavior, but on his oscilloscope, he can still see it happening. And so in a way, we're asking for trouble by setting that instruction register on the rising clock edge. Now, of course, we have to set it, and we can't really set it on the falling clock edge because, well, the rest of our computer is synchronized to work on the rising clock edge. So that RAM chip will output on the rising clock edge. If we do it on the falling clock edge, then you know, we could have all kinds of other problems because on the falling clock edge, these signals will in fact change. And so perhaps we'll only write half of the signal into this. So that's not really a solution either. And so what I've come up with, we can see here on this diagram, I've basically introduced a sort of a 2-step process. So whatever is on these instruction register lines here isn't actually going directly into the EEPROM. It's going along these green lines to another register chip, which is here, which is in fact a 72HCT273. And so that register chip, which is this one, 74HCT273, that works very similarly to our 377. The major difference is that it doesn't have its own write enable. So it in fact always latches whatever is on these D input signals at the moment when a clock pulse arrives. And that's what we want, because all we want is to delay the change of that instruction register by half a cycle. So what we want is the new instruction to arrive in the real instruction register up here on the rising clock edge. And then when the clock falls down again, at that point, we want this mirror register or this secondary register to take the new contents of the instruction register at that moment of the falling clock edge, because then we can drive the EEPROMs using the output from that register. So all we need to do is hook up these inputs to our actual instruction register outputs, and the outputs of that secondary register we are going to connect to the address lines of the EEPROMs. And so that's what you see here. You see the instruction register coming into the 74HCT273 and its output going into the EEPROMs. And the clock signal is in fact the inverse of the clock signal. It's that same inverted clock signal which is going to our timer. And so that is how we make sure that at the moment when this timer changes, i.e. on the falling clock edge, is also the moment we do all of our changes to the address lines of these EEPROMs on the falling clock edge. So that goes for this timer, and that also goes for the instruction register. And so now David Courtney's problem, it really isn't theoretical. I had the same problem myself. So without that setup, I initially just wired this instruction register directly to my EEPROMs. And I was finding that this program counter was counting at moments when I didn't expect it. And so searching through and remembering in the back of my mind that I had seen something about that somewhere on YouTube, and it turned out that that was David Courtney, reminded me of the fact that these EEPROMs, yes, they can actually fluctuate and send spurious control signals during the time when their address lines are changing. And so that's how I decided to be very strict or draconian about only changing the contents of the address lines, or the values on the address lines, on the falling clock edge by using this two-step instruction register setup. Now, of course, the last two input lines to our EEPROMs are the flags. And the flags register, as it is here, has exactly the same problem. Those flags change whenever the ALU latches, when this ALU write signal is enabled, and the contents or the output value from these 74 LS382 chips go into the register, and the flags are set in this register. And that happens on the rising clock edge whenever that signal is enabled. And so once again, if we were to wire those directly to the control logic, some of the address lines would change at the moment of the rising clock edge. And once again, during 150 nanoseconds, we might get spurious signals on these control lines, and we don't want that, certainly not on the rising clock edge. And so for this register as well, we have exactly the same kind of setup. So we have our 4 flags coming in from the flags register here. And once again, we have a register. This is a 74173, which is the same as a 273, but it's 4 bits. And its clock is also connected to that inverted clock signal, which is also driving our timer. And so you can see very clearly here that wire, which comes from the inverted clock signal into our primary timer, is also driving this flags, this secondary or mirror flags register, as well as this mirror instruction register. And so it's the outputs of those which are driving our EEPROMs. Now, the last thing I want to talk about while we're discussing the hardware of the control unit is some properties of these control signals themselves. So you'll notice that many of them actually have a bar. They are active low signals. For example, this write register C. And that's because when we've implemented these components, it turned out that the chips in question were expecting an active low signal. And so Beniter, when he builds his control logic, he has some extra inverters here, which will allow these EEPROMs to always output active high signals, and then he inverts those that need to be inverted. But since we have to program these anyway, that's sort of an unnecessary step, and it creates extra logic which we don't really need. We can simply program these EEPROMs in such a way that, for example, this register C write signal actually outputs a 1 in its default configuration and will output a 0 at the moment we want that signal to be active. We can program our EEPROMs to do that, and in fact I've done exactly that. The only problem with that is these LEDs. So if I were to then naively connect all these LEDs to show precisely which pins are at 5 volts and which are at 0, well then I would, when I'm looking at this, need to remember that the signal is active high or active low, and if it's active low, I would need to look for this LED to go out. And so I haven't done that. I've actually, if we look very closely, I've actually reversed the way these LEDs are connected. So for example, this LED, which is connected to the memory enable signal, is actually connecting the pin from the EEPROM to 5 volts. And so if that's at 5 volts, i.e. when it's not active, that LED will be off. That's, for example, the case here. So what that means is, because that's connected to 5 volts, that means that the output pin, which is indicating a memory write signal, is high right now. But this one is low. And because it's low, I've actually created a potential difference between the pin and this 5-volt rail, and that's why the LED is lighting up. And so all of these LEDs which are connected to active low signals are actually connected to the 5-volt rail. Now, once again, this isn't really 5 volts, so you'll remember that certainly these EEPROM chips, as well as most of my HCT chips, actually need current limiting resistors. And so once again, I have this is the actual 5-volt rail. I have a current limiting resistor on here, which is being shared by all of these blue LEDs, which are connected to the, let's say, high signal. So in fact, this is probably around 3 volts or somewhere. And that ensures that we don't have too much current going through these LEDs. Now, some signals are, of course, active low. For example, many of these ALU signals here are active low. And so if you look very carefully at those LEDs, they are actually connected to the ground rail. But then these here are connected to the 5-volt rail. And this one, which is active low, is connected to the ground rail. And so these EEPROMs, they know whether a signal is active low or active high. They've been programmed to send out whatever the component requires. And in order to show some sort of a consistent display to us, the user of this computer, I've simply reversed these LEDs whenever we had an active low signal. And so that pretty much concludes the tour of our control unit. So we've understood pretty much everything that the hardware needs to do. So the central component are these EEPROMs, which we've programmed to send out correct control signals and taking into account whether they're active low or active high, based on the inputs from this counter, which is provided by just 74 HCT 161, and that counts from 0 to 7, based on the input from the instruction register, and based on the input from these flags. But both the instruction register and the flags are not connected directly to the inputs of these EEPROMs, but they are in fact slightly delayed, so when they change half a cycle later on the following falling cycle, these mirror registers here will in fact change the values on the address lines half a cycle later. And we do that to avoid these address lines changing at the moment when we need them to be stable. And then finally, for the flags register, the carry flag is connected directly to one of the address lines, but the other 3 flags are combined with the last 3 bits of the instruction to sort of enable us to multiplex a single instruction to nonetheless depend on a particular flag of our choosing, depending on which one of these bits we've set in our instruction. And so using that technique, we are able to use only a single address line into the EEPROMs, in fact the final address line we have available, to provide nonetheless 3 different conditional jump instructions. So what I want to do in the next episode, now that we've understood how the hardware of this control unit is set up, is to actually look at the microcode which we've used to translate our instructions, which we have here, into the series of control signals which are required to correctly execute those instructions. And so that will probably be the last video about the operation of this 8-bit CPU. So I hope to see you then.